we're going to go to the next presenter, Xavier de Kestelier. Xavier is head of design technology at Hassel studio, where he leads design technology and innovation across all disciplines and regions. For the last decade, Xavier has been an industry leader in the field of parametric design, digital fabrication, and additive manufacturing. He was co-head of Foster Partners internal research and development team, where he worked on the Apple headquarters, Kuwait, and Beijing airport, as well as NBK headquarters. At Hassel, Xavier is developing the practice's global digital design strategy for computational design, building information modeling, visualization, and virtual reality. Alongside this, he is developing technology for cross-studio design review processes. In recent years, he has built up a portfolio of architecture in the extreme environments, with a particular focus on space with Habitat project for clients such as NASA and ESA. Xavier is also a director of Smart Geometry, which most of you know. Xavier has held academic position at Syracuse University in London, University of Ghent in Belgium, and the Bartlett University in London. So I'm going to leave the screen to you, Xavier. Welcome.
Thank you. Thank you. Let me just share, see if that works. Does that work? Yeah?
It does indeed, yep.
Everyone can hear me as well? That's great. Hey, thank you so much for having me today. It's been a long day, but it's been a really interesting day, I thought. We're going a little bit further. So, this is probably the most important picture ever taken. This is Earthrise. Picture is taken just over 50 years ago on a Christmas Eve, and it was taken by astronaut Bill Anders. Bill was one of the astronauts of the Apollo 8 mission. Apollo 8 mission task was really to kind of prep for the later Apollo landers on the moon, and the task was to take pictures of the landing sites on the moon. But when Apollo 8 came from behind the moon, from the dark side of the moon, it suddenly saw Earth, and that was that picture. No, that wasn't actually the picture, because this was a picture that got published. The real picture was really this one, because of course it was flying around the moon. But for some reason, it never was published like this. And I always kind of wonder why that is. Is it because Earth really looks too fragile, too small in this kind of vastness of darkness of space? And the effect that that has, seeing Earth like that on astronauts, has actually a name. It's called the overview effect. And what it does, a lot of the astronauts actually become climate activists after they come back to Earth. They actually kind of see the importance of the environment. And I had a little bit of an overview effect myself. And I didn't go to the moon. I went a bit further. I actually went to Mars. Of course, didn't really go to Mars. I did a project on Mars. So this project was for NASA's 3D Printing Centennial Challenge. The task was to design and imagine a 3D printed base on Mars. Now, as an architect, you know, how do you start something like that? Because really, this is, you know, this is not an architect's field, right? This is really literally rocket science. And the examples that we have out there aren't too many. There is, of course, the International Space Station. When you look inside the International Space Station, you kind of really quickly realize there haven't been many designers involved, I would say. I'm not sure about you, but I wouldn't really want to spend that much time in a space like this. So what kind of references do we have? And as you work in space, you often might think that, well, you know, we do have references in space. There's loads of sci-fi movies out there, right? That give great examples. You know, Star Trek, Space Odyssey, Aliens. One of my favorite ones, Moon. But for me, these are not really the great references of design in space. I like to look at real designers in space. Now, Fortunately, there aren't too many, but I'm going to show two. This is Galina Balachova. She was the only female architect in the Soviet space program. She was also the only architect working in the Soviet space program, mainly, I mean, in the space modules section. And I love her work because if you look at her drawings for the interiors of the space habitats, they are of a completely different level. They are almost homely, I would say. Using completely different materials, different shapes, different ways of looking at an interior of a spaceship. She even worked on the Russian moon lander. Not a lot of people know this, but the Russians did have a moon lander that almost got launched. I think one of them actually flew in orbit even, and that was a lander for one person. And that was one of the drawings that Galina did for that lander. She did work on stuff that was that flew, of course, Mir space station, and these are some of her drawings of that interior and her designs. So Galina had a particular way of looking at design, I think, a more human-centric perspective in space. And another person had a more human-centric perspective was Raymond Loewy. Raymond Loewy, industrial designer, he came on board of the design of Skylab. Skylab was the first long-term orbital station from NASA. And they brought in Raymond Loewy, who's, of course, the famous American industrial designer. And they were quite skeptical at NASA, the engineers on the team. They were like, well, what is this designer coming to do on our, you know, in our team? What are you going to do? Choose the color, right? Well, he did choose the color, but he did a few other things, which were quite fundamental. He designed this table. You might wonder, okay, it looks kind of a cool, funky table, kind of a techie table. What's so special about that? Well, in the original concept, the engineers of Skylab had just designed a little kind of tablet that would come from the side wall of the of Skylab, where the astronauts could eat from. So they would each of them sit in their own little corner facing the wall, right? They weren't going to be able to have a conversation, right? So they needed really a designer to come in to say, hey guys, we actually need a table. Astronauts might be able to kind of want to have a conversation about how their day went. The second thing he put in, and you see it on the picture here, is in the background, that window. Okay, circular window. Nothing special about it, right? Well, there is something special about it because original design did not have a window. It's because it was just a risk for the engineers, right? So they didn't think the astronauts needed to see a view of Earth. But imagine going around Earth for weeks and months and not seeing this. So because of that, I feel as designers, we probably do have a role to play in this field of space architecture, and we should not leave it only up to the space engineers. So Mars, how do we start? How do you really start to design something on Mars? Well, I think it's just the same thing as designing something on Earth. You just look at the environment and where you are and what the environmental factors are. So where are we? Well, this picture is relatively correct in scale, the distance of Earth to the moon. But that took 3 days. I was quite surprised how far it actually looks like, right? It's about 300,000 kilometers. Now, the distance to Mars is 1,000 times that distance. So imagine taking that distance that you'll see this on your laptop, wherever you are, and take that 1,000 times. And that's the view that you get from Mars. There's a picture taken from the Curiosity rover looking back at Earth. So we're just this tiny, tiny dot. So anything we're going to take, it's going to take a long time. It's going to be very expensive to take. So we're going to have to pack compact and light. Whatever we're going to do on Mars, it have to be light and compact. Other factors that will play a role. On Earth, we have something like the Earth is magnetically charged, which is great because actually it creates a field, an electromagnetic field that actually protects ourselves from radiation, cosmic radiation and solar radiation. Now, on Mars, we do not have that. So the problem there is that we get constantly bombarded by cosmic, galactic, and solar radiation. So we're going to have to protect ourselves from that. It's a very important thing. So what else is there? What other environmental factors do we have? Well, it has an atmosphere. Mars is a CO2 atmosphere, mainly CO2. It's a very thin atmosphere. So it's about 100 times thinner than on Earth. It is quite thicker, as in the depth it is thicker, but the density is much less. Pretty cold, let's say roughly -70 on an average day. And we have 1/3 of Earth gravity, but that's more fun than anything else. Mainly the structural engineers love that, because and the architects, you can make stuff much thinner than on Earth. So I already said we better pack light to Mars, so we should also use as much local materials as we can, a bit like we just heard about from colleagues at WASP, which I found a really interesting presentation as well. So we're going to use local materials. What do we have locally? Well, we have regolith. It's local Mars dust. That's what we have. So how are we going to deal with that? Well, this here actually shows our main concept. Our main concept is on the outside, we have this layer of regolith, here in case it will be 3D printed, and that will be there mainly to protect our inhabitants or our astronauts from radiation. On the inside, we're having this inflatable, unfolding and inflatable module that is there to regulate the temperature, but also regulate, of course, the oxygen. So that is a kind of a pressurized volume, right? So that's actually where the astronauts can live. And this is how we're going to print it. Of course, you know, we're going to go to Mars. This is going to be quite a pretty big volume that we need to print. We're not going to bring a massive print. That would be too heavy and too complex. So we're thinking of maybe going the other way and creating this swarm of robot printers. Right? And here they are. We have 4 different types of robot printers. We have diggers, we have scouters, we have transporters. And before you think then we just made all of this up, well, we did make up quite a bit of it, but some of it, like the digger, is actually a prototype that's being developed by NASA at the moment. It's quite an interesting digger because it doesn't use its own weight to be able to dig into the regolith or the sand. In this case, it actually uses 2 counter-rotating drums that actually almost digs the digger into the earth, and that way it can actually pick up quite a bit of regolith. This was one of the first renders we got back from our visualizer. I love this render. It really shows what we're trying to portray in this design. But one thing kind of shocked me, and it was on the front, on the right-hand side there, you see all our printers who have done their job, who've printed our habitat, and done their job, nothing else to do. So we've just created a first boneyard of robots. And that was a bit of a shock, you know, we just arrived on Mars, printed something, and we created lots of rubbish. So I thought that wasn't really not the right thing to do, back to the drawing board. So we came up with this. We thought, why not have a robotic system that is adaptable, that is a modular system, and we can really, it's a bit like a Lego system for robotics. So why can't we just have different elements that fit together and are able to create different types of robots? So you have a battery pack with solar cells on a wheel, you add some more wheels, you add some diggers, you suddenly get our NASA digger, but we can also add other modules so it can become a printing module, right? And you can see that here, a little sketch here to show how, you know, the modules wouldn't, of course, not fly from the sky, how this system would be able to pick up certain elements and be able to kind of self-assemble any type of these robotics. And a little video of that, our one-wheel scouter, looking for the right regolith, then our digger, digging itself, as you see, it counter-rotates into the ground. Our sieving station, where it gets, the regolith gets refined, and then we have our printing itself. Now we're using microwave technology. Again, you know, it's not completely sci-fi, I would really call it sci-fact. There's lots of research institutes looking at the moment if you could microwave and sinter regolith, or whatever we find on Earth, which is often basalt type regoliths. So that we came up with this kind of robotic system. We thought, well, actually, it's a bit unique. It's a bit different, right? And we see it sitting in between these two extremes. We're seeing it in between this very pragmatic and productive Tesla factory with lots of robotic arms. Each of them have one very specific task. It's very efficient, but there's a very low redundancy. You know, if one of these robots fails, you have to bring in another robot that does exactly that same task. On the other hand, you have swarm robotics. I think there's a project by Sheffield University that, you know, like ridiculously high redundancy. You can throw half of the robots away. They will be able to do the same task, although they're not always that pragmatic and functional, these swarm robotics. So we believe we somehow sit in between in our robotic system, that there is a high level of redundancy available, but we're still quite pragmatic and functional robotics. So this is our habitat. We have the shell structure and under that protects us from radiation, and underneath we have our inflatable, unfoldable habitats. Now the shell structure itself is, we worked for this with Xavier Callaghan engineers. That was form found. We didn't really design it. We kind of optimize it for compression only forces. Great thing about Mars is that you don't have to take into consideration too many lateral forces. Although there is really high winds of 200 kilometers an hour, the effect it will have on the structure is very low because the density of the air is so low, right? So mainly compression only structures we were able to design. Now you saw in our 3D printing little video before this, we didn't use any support structure. Well, that video was early done in the process. So we needed a support structure. We thought, well, let's do something lightweight. Let's do an inflatable support structure. So we have this kind of inflatable structure here, which is then used as a scaffolding really for our printing of our shell structure. We kind of thought this was a bit big, and still we said, yes, we're traveling light. This isn't really traveling light, right? We also bring this massive structure that was only used once in the construction process. Again, not a very sustainable way of thinking. So we rethought that. And we just, that's some inspiration from Earth projects. There's Toshima Museum from Sana. That was done by using Earth formwork. So it used Earth as a way to really, as the scaffolding for the concrete. So we said, well, why don't we do the same? Why don't we fill up the whole dome structure here also with loose regolith? And at the end, we actually kind of excavate it afterwards. It does look a lot more work, right? But luckily we kind of, you know, did it all parametrically. So we're able to kind of calculate how much our printing time was and how much our kind of excavating time was. And we did that not by ourselves. We actually also worked with the students from the MSc in space engineering with Professor David Cullen at Cranfield University. So these students were working with us in parallel, really, while we were doing the design. They were working on lots and lots of spreadsheets to kind of understand how much energy everything would take, how fast we would go. Also, they actually looked also at, besides the architecture, which we were leading, they also looked at the mission architecture, right? How many launches do we need to go in orbit? How many kind of one-way or return trips do we need to go to Mars to deliver all this material, right? We were able to kind of, you know, doing this Earth formwork or regolith formwork, we figured out we need an extra year. And one thing we have in space is time. So we thought that's probably the right way forward. So the other big part of our design was, of course, inflatables. And you might think, well, inflatables in space, is that really possible? Do you just kind of get it from a sci-fi movie? Again, no, not really. All of the things that we've kind of added in this project somehow already exists. So inflatables in space, it exists. NASA's been looking at inflatable habitats in space since the 60s. This is a research project they did with Goodyear. In the 90s, they developed this TransHab, which is again an inflatable module for space, for low Earth orbit. They actually sold the patent and licensed it to a company called Bigelow, and they went and developed an inflatable habitat pod, a small pod for the International Space Station, which I think is still attached to it. So this is an astronaut actually in that inflatable pod. So our habitat really exists out of these 6 pods, really all with a radial organizational system. It's a system of racks that are also, you can move the racks along the circle. So it's a modular system, so you can turn any module into any kind of function, right? So it's a very kind of adaptable modular idea. And this is our how we believe the habitat would look like. On the inside, sitting under that shell that protects yourself, looking through a courtyard to the other pods in the habitat. And I know I said we were going to travel light and compact, and you're probably wondering that furniture does not look light and compact. But the idea was for us to also kind of manufacture stuff as much as we can on Mars. So the idea was to 3D print the furniture there. And the real idea was to kind of use recycled plastics, right? So there's food packaging, there is packaging from science experiments. So the idea was to kind of, that waste plastics, we use that to actually 3D print objects that the astronauts might need. We didn't just want to make a picture of it, we actually wanted to kind of do it for real. First of all, we imagined it probably would be not a heavy industrial arm, it would be a lightweight Delta printer. This could become the first WASP printer in space, maybe. So you see it on the background on the left there. And but we did it also on Earth. So we worked for this with a company called Nagami, with the founder Manuel Garcia, and they have he has a company in just outside Madrid where they 3D print furniture and larger kind of installation pieces. So Manuel was really nice. He got really excited about it, and he actually designed one of these chairs that would actually feature in our Mars habitat. The interesting thing about this design is it's actually quite lightweight. It's actually one layer of plastic that is being 3D printed. So it's quite efficient. And there you see that chair. And we're very lucky because we were able to kind of exhibit the whole project at the Design Museum just before the pandemic hit. So we did make our own inflatable. We worked with a company in Ljubljana for that. We had Manuel printing all the furniture. And we also had a big screen, a big kind of, that would show us in real time what that view out to Mars would look like. And this is that kind of racking system that when you went there, maybe some of you went to the exhibition, you were able to kind of move these racks around as well. I think to finish off, I hope I have a few more minutes. I'm just going to show a little video, but do let me know if you do not hear the audio. I hope it works.
Half a century ago, we took our first step on the surface of the moon. Today, there is renewed passion to explore for our next human endeavor. Mars, the red planet, further than any human has ever been. We face many challenges: remoteness, no livable atmosphere, high radiation, dust storms, and extremely low temperatures. Before any humans set foot on Mars, we must first design a protective shelter. We will protect our astronauts from radiation with a thick 3D printed shell structure using Martian regolith, which works great in compression but does not perform well under tension. To overcome this shortfall, we have chosen to construct the pressure-retaining parts of the habitat from lightweight inflatable pods. They will be made out of high-precision engineered composites that are prefabricated on Earth. Their elliptoid geometry will be able to mitigate the pressure differences whilst optimizing spatial planning. To create the base on Mars, we will use a two-phase approach. In Phase 1, an ecosystem of 3D printing robots will arrive months in advance of any human explorer. They will construct the protective shield for the base by adopting a modular robotic swarm strategy, a plan that allows for redundancies and enhances the odds for success. Intelligent autonomous robots will have interchangeable roles, from battery storage to scout rovers, logistics to excavational, and even 3D printing units, all integrated with multiple cameras and sensors for navigation. They can reconfigure themselves for a multitude of purposes, ensuring prolonged usage beyond the initial build phases. The smallest configuration is the one-wheeled scout rover that uses ultrasonic scanning to analyze the Martian surface to determine the best regions for obtaining optimum regolith. The digger receives the location coordinates and then excavates the Martian soil. It then delivers the payload to the refining assemblies. Here, large chunks of Martian regolith can be processed down to a finer grain and then delivered to the melter robots in situ. They then use concentrated microwaves to melt the regolith and extrude through the 3D printing nozzle. The shell is autonomously 3D printed, layer by layer, over several months by the robotic system. In the next phase, the first astronauts arrive with the habitation units, equipment, and supplies. The robots now take on their second life roles to aid the next phase. They come together to make flexible mobile platforms that can carry the payload from the loading zone to the base. The convoy begins its journey across the Martian surface to the habitat site. The build commences with a connector module placed underneath the protective shield and ready for inflation. The module then unfolds and self-inflates into its final form. The habitation units are then placed into position and sequentially inflated to form the completed pressurized environments. The circular layout of the habitat ensures continuous accessibility of the habitat in the event of a catastrophic failure. Each connector module houses 3 integrated environmental control life support systems, delivering essential services like power, water, data, and oxygen to all the habitation units. A circular conduit delivers these services to multiple endpoints in each pod. The base will be remotely powered by 2 nuclear kilopower reactors and a solar farm, located a safe distance away from the base. In the next stage, the astronauts will construct and install a flat-pack, rail-based racking system capable of connecting to the distribution system, enabling spaces to reconfigure according to their spatial needs. This modular and radical design principle has been adopted for all the habitat pods, ensuring multi-use, reconfigurable environments. A Martian base should not just be a habitat. It is home for the astronauts. Each pod expresses its own identity, quality, and character. A highly functional design which places the human experience at the core. Spaces include a state-of-the-art research laboratory, a hydroponic greenhouse, a fully equipped workshop with digital fabrication facilities, the sleeping quarters with gym facilities, and immersive virtual reality platform. We believe that the key to success of human habitation on Mars is the health and well-being of its residents. Creating a place where work, life, and living combine holistically to ensure they feel connected to each other, to themselves, and somehow to their distant home.
Thank you.
Thank you. Well, great presentation. A lot there to start. I'm going to start with one, and I guess you will be bombarded with a lot of questions right after me. So my first question is, obviously, with being on Earth and having access to material, we test 100 times before we manage to get the print going. How are you guys thinking in that trajectory? Like, how are you doing printing tests in advance, or what are your possibilities here?
Not a lot, right? So the interesting thing is that you know, nobody have a sample of Mars regolith on Earth. It doesn't exist, right? There are missions out there now, right? I think is the ExoMars mission. I think it is that one that is now actually drilling in the Martian surface going to take a sample of regolith and drops it behind it, the rover. It just drops it behind it, and there will be samples ready to be picked up by future missions that will go. It sounds all a bit crazy. That there's another mission going to Mars. It's going to pick up these samples. It's going to shoot itself back up in Mars orbit, where it then will actually kind of transfer that to another vehicle to come back to Earth, and all that without contaminating anything. So that's going to be, yeah, the first sample of Martian dust will arrive on Earth, I think, in 2030s, early 2030s. So a bit far away still. So the better thing to do is, of course, we use moon regolith. We know a lot about that, so that we'd be able to kind of test with. We know what moon regolith is like, so for that we often use moon regolith simulants, which you can buy online even, and that's often stuff that you can find from volcanoes. So it's kind of close to what the regolith is of the moon. So yeah, there is some, but I'm very much aware it's not for tomorrow. Yeah.
Right. I mean, it's just a question that I've asked myself a few times. Every time I sat at the NASA presentation of the next, next proposals to come in, and with the swarm intelligence, I mean, the swarm robots, it's quite interesting. And have you guys also applied any simulation to see how long does that take, assuming we are on the Earth, let's say, using those swarms, how long would that take to print the shell?
It was about, we did some simulations, and it was about 3 years for it to print, but we got time, we're in space, who's waiting, like, we're not bothering anyone, are we? So yes, it will take a long time, but the complication of you can do 3 years before astronauts arrive is much better than spending astronaut time doing that, because they're there to do research and science, and they're not there to build. So you better do it that way.
And I'm going to ask the worst awful question. You're not going to use water by any chance for the project at all?
You could use water, but it's cold, it's frozen the whole time.
No, I'm just asking, I'm wondering, because
no, we'd be microwaving it at the moment. We kind of decided to do a system where we don't need to use any binder, where we just use energy and regolith at the moment.
And basically just laser it and bind it that way.
Yeah, you microwave it together, so it is possible. We've got some other ideas as well. We're working. It's a kind of a continuous project, really. I see it. I started doing some of the work back at Foster & Partners. I'm continuing that now, and it's a continuous research thing. We're now working on 2 projects for the European Space Agency. Well, one of them where we're really looking at this idea of modular robotics. So they asked us to kind of take that part of our Mars project and look at that modularity of robotics and construction for the moon. So that's one thing that we continue to do. Now we're really interested in, we've always designed singular pods, right? And most of the designs we've done, we're now interested in, well, what if you grow a base? You saw maybe in the video, in the last shot of the video, you see the base growing.
Right.
It's a bit of nonsense, really, because it doesn't quite work like that. It was good for the video, but it doesn't actually work that modular yet. And you would actually have to take away part of the 3D print and then re-3D print other parts. So that wasn't actually worked out yet. Also, I don't believe that you create a community somewhere by just copying the same type of module over and over again. A village doesn't exist out of the same modules. A good urban community doesn't exist like that. So we're now looking at what would a future moon base look like? What kind of modules do you need? How would it grow? How would it grow from 6 astronauts to maybe 150 astronauts?
Oliver, thank you.
Yeah, Xavier, thank you very much for that awesome presentation. And I have a question for you, and I'm not quite sure if it's the right one for you, because what I just learned is you really take that serious. You develop it further. I know previous presentations from maybe 2-3 years ago. It's developing and it's you have clients, right? You have clients for that, if I understand.
Yeah, me too.
Yeah.
Me too.
So then, and I'll still ask the question. Do you also have the ambition to take the learning back to us? Like a lot of these things, you said it yourself. There's a relation to the previous talk about WASP and their approach. Is there something that you take for maybe solving our pressing problems of resource scarcity on our planet?
Yeah, no, we do. It's a bit annoying because there's 2 projects I can't really show yet. It's not out of the press yet. So I'll have to come back then, right? The first question is, yes, we do have clients. You know, when you work for NASA and ESA, these are often kind of research projects. But we do work now for a kind of space engineering firm where we are designing habitats. So yeah, it is for real. And we are bringing back to Earth. Yes, well, you know, we kind of used the printing process that we've kind of learned a lot of from Nagami, their printing process that uses recycled plastics, uses BTG plastics. So we're now looking at using that in architectural applications. So hopefully, around about next year, or in 6 months' time, we will have our first building printed like that. And that would be done only by recycled plastics. We started to kind of think about this at, we were invited just about 2 years ago for a robotics workshop at Norman Foster Foundation, where we started to kind of play with this idea. Can we use this process at an architectural scale? And now luckily we found a client, and hopefully in about 6 months' time, you'll see something of that. So yeah, we do bring that stuff back to Earth somehow.
Yeah, we'll get you again for a lecture in 2 years since hold it.
Yeah, I mean, it's kind of fascinating with this NASA project. Well, I mean, I actually think 3 to 4 years is quite long, especially with the proposals that is being asked every year. And this year, NASA had 2 trajectory for either printing on Moon using only Moon. Was it Mars or Moon? I can't remember which project was it that used only the local material, and the other trajectory would be to bring material from the Earth and build, and you would not hybridize it, and you would just think either or, which was quite interesting to see that they actually initiated 2 separate trajectories and wanted to look at the proposals that comes in. But how do you see, I mean, what do you see in, I mean, both you and the previous presenter are working with local material, but in a very different, with a very different machinery system. So what do you see that you could take from them versus, or they could take from you guys in both cases?
Oh, we both need to answer that one, don't we?
Yeah,
what I really liked Lepa's presentation was your gantry system. How I wasn't aware that you have these kind of different types of you know, putting the framework down and then being able to having different coverage of the building. I think that's actually a really interesting one. It's also a super lightweight one. So I think there's really applications in space for that, because think of it, you know, you have 1/3 of the gravity on the Moon, you have 1/6 of the gravity. So you can actually do massive long spans really easily, you know, with less deflection that you get on Earth. So these kind of very thin systems, lightweight systems for gantries is actually quite a good proposal as well, I think, for space.
Right.
Can I add something?
Please.
I agree. I think that yeah, this could be the future, because I'm super fascinated about the use of storms of robots that made different things, but are very similar robots, no? and probably is very nice to understanding or try to thinking about a kind of architecture that is not related to the reduction of the use of material, no? Because if you imagine a storm of robot that can work 24 hours a day, you can create a total different shape, not optimized by the using of the material, but probably optimizing by the use of energy. So probably is better to use a lot of material with the small robot that don't use a lot of energy. So probably we have to totally rethink, and it's very nice to see a project like this that have totally different relation, no, to the local condition, because it's based for Mars. Yeah, thank you for your work and for your presentation, because probably this could be the future. In our case, we love this because we use Earth, and when you use Earth, you need to replace Earth on your building each time during the time, no? If you have some problem related to the rain and something like that, you have to replace the soil. So it's very nice to thinking about storm of robot that can help you to replace each time autonomously the earth on your building. So I mean, for the maintenance of the building, this could be a super nice option.
Also doesn't rain on Mars, which is great.
But then how do you get the energy for the robots? Is there enough solar energy? Like, are they all running on solar panels somehow? And then you show that it is what, microwaving the Mars dust, or
yeah, you need about 1,000 watt to do it. So it's kind of, you don't need that much to do it. So it kind of works. There's some research done on that. Not usable machines yet, but the testing have been done. You could do it. Yes, you do need energy. Solar PV cells are they're usable. We need a lot of them, and you are further away from the sun, so they're less optimum. There are big storms on Mars. The problem with the storm is it's not that you're going to fall over like Matt Damon in The Martian. That can't happen. But what it does happen is you get this dust, a dust that actually just like a cloud, like a mist of you get that, and that will settle down, and that would actually kind of decrease your solar cells. But it do have NASA is working on some portable nuclear power, as you saw in the video as well. So that is probably the best solution. Nuclear power for space. They're looking at nuclear propulsion as well now. It was a bit of out of fashion for a long time, but that is all coming back. You know, so nuclear power is probably a good solution for a lot of things.
I'm afraid we slowly have to wrap up the symposium.
I had one last question, if I may. I just had one.
Me too, but go for it, please.
15 seconds.
Super. This is great. Do you have actually conducted experiments in like this depositing or heating up in other gravitations, like in Mars gravitation and gravitations? If it actually works like just on Earth, or are there?
Well, it's a bit hard to kind of simulate gravity, of course, or lower gravity. For that, you need to go in these parabolic flights, and that only lasts for a few seconds each time. So we haven't done that. But I'm a designer. I just rely on existing research that is out there by other research institutes to get inspired by, and kind of take those. If I see something exists, reach out, extrapolate, and brings it to our design process. Although we are looking now for ESA, of course, on the modular robotics, so that will be something that we'll be testing, but not in the environment yet. We did many years ago. I did test some 3D printing in a vacuum with lunar simulant. So I did do that once, but most of the time I kind of stick to what I'm hopefully good at, is design itself.
Really cool.
You said you're a designer. Very last question. You stressed the role of the designer. This is a very interdisciplinary thing. you have experience in maybe more conventional interdisciplinary teams. Are space engineers more open to designers coming with narratives because it's so much driven from ideas of science fiction as well? Are they used to crazy ideas that become reality?
What am I going to say?
They're your clients. Take care.
People are getting more and more open to it. Let's say that. I think the interesting thing is the process I normally go through is that people come to us because we made something very pretty, right? We made a pretty video or we made fancy images. But what's interesting is that it's our role to actually explain that a pretty image is not just a pretty image, it's actually kind of a whole design process behind it. And it's our role as designers and architects to explain what that value is and to show what that value is. And that's the process I normally go through. And once you do that, people go like, oh, right, that's what architects do. That's what designers do, right? Because, you know, it's not very clear sometimes, and we're very bad to explain to the world what we really do, right? So you can only do that by doing, I think, by going through a design process with a client and showing where our value really is. And our value is that we're able to kind of step into any world, right? And being able to kind of take and understand what the technologies are and the technology readiness levels are and what the constraints are, and still being able to kind of do something with that without feeling too constrained because we feel that we can't do something because we already, some engineers know too much, of course. They can't actually step back and, you know, take overall, I would say, design decisions. And that's what we're good at, you know, not knowing enough. I think that's what we're good at. Or not knowing too much. We know enough, but not too much, which is good.
Thank you very much, Xavier.